Okay, hey, train your plants every day. Jordan Scoville coming at you from the STEM Lab. So, generally one of the things I like to do is I like to study mathematics and physics and things like that. Um, Generally speaking, I usually give you a more quantum dynamic theorem on the physics side of the principle using psychology and physical references, stone dock, training plants, whatever that may be. Would be physically training your plant to know the grow model, to be a botanist in Harvard, know the mathematics and spectrums and Higgs fields, and whether it be spectrums of light or spectrums in the STEM models of what degree or distance from the plant you're dealing with and what have you. But I really wanted to get one into mathematics. Now this one's I've been kicking this one around for quite a while, and I've far from caught this rabbit, but I've certainly been chasing it for a long time. Um, so what I want to give you is kind of the general nature of what you're looking at mathematically. Um, Whether it be, I think more specifically, when you're looking at some of the higher concepts of mathematics, when you're looking at very complicated equations, for the most general people out there, ones you look at and kind of go, I have no idea what any of them symbols mean. I don't know what any of these references go to. Product rule, air turbulence equations, Schrodinger's work. You crack open a general relativity book, you see the E, the K, the R, the capital pi symbol, the sigma symbol for some and what have you, the little environment, and they can mean a lot of things to a lot of people. But one of the, I've like I said, I've been hunting this rabbit down for quite a while, and I've managed to pick up a hair to the wily hunter that I am. And so you see a lot of clues, you see a lot of tracks out there, and kind of what they're referencing, and what a lot of this stuff talks about. So with that being said, you will see a lot of these things. They kind of compound themselves. Some, well, why not just use equal? Why not just use, um, a gradient is addition to this factor. A lapicant is this subtraction from this idea. A gradient is an upward triangle. A lapicant is a downward facing triangle with a little extra on the one side, a little more meat on that line on the one side of it. You get them fancy A's over divisibles and K and pi and what have you all the time. What is the need? Why would you need something like that when algebraically speaking it's A plus B essentially, and a lot of times that gets confusing for a lot of people. So I'm going to show you the problem with some of the natures of just the algebraic system of thinking about that. So what I have here, we're all in trouble now. Homework, right? I don't know how well you're going to be able to see this, is just some basic algebraic system. This is the XYZ principle. So when you think about a logic problem, when you think about how to logically create this system using dimensions, laid out on paper like this, you have a problem. Firstly, which direction do you travel in first? So what you have to do is firstly say, well, if we're going to continue in any direction, we're going to have to pick. We're going to have to choose which dimension over all others comes first. So usually I'll start with the American model. It's just the brain works that way. We'll travel right to left. I don't know how it's orientated here on the paper as I'm doing this, but as you write right to left. You start at right and you move left. And that's the X dimension, X, Y, Z. We'll get into that here in a second. Infinity, X, Y, Z. Because eventually, alphabetically, you're going to travel A, B, C, D, E, F, G. But it's more complicated than that. Once you get to Z, you could go A1. Or you could just start with that from the initial concept. A1, and then move into whatever pattern or orientation that is relative beyond those ideas, and whatever sequence you want to start with. A, we're going to start in this position. A is away from that in the 0 position. A, because we're doing this dimensionally, can be in any field of that. You have to think about that idea. and some realistic things as you deal with them in defining where you really are mathematically. You got to take things like, well, why do I need an equal symbol or the sum amongst a series for a symbol that references what those things correlate to? And it's because of this problem inside of a series. Each of these are individual series as much as they are one universal system of how, well, it's not really, it's too complicated here to really define really what's going on, and it explains nothing. Physically, when you're talking about a product in the Stone Docker, McDonald's, and this isn't going to get you far, but yeah, this is everything you deal with. You're starting here, and I have to talk about customers, and I have to talk about employees. Which comes first? Yeah, when you're looking amongst the sum of a series, we're going to pick a direction, and you're looking at that mathematically. So in the product rule of what you're dealing with, or with an integration feature of those, how they affect each other, we're going to choose a dimension on that idea, and we're going to say that's a series. We're going to say that in that series needs some simplification instead of a complete understanding or a complex variation. Because even though this looks fairly simple here with numbers and x's for positions, we don't always know that one starts there. And we're not always going to say that it follows a very simple logic problem like that. We're not going to say it just travels infinitely like that. Here it's just going 1, and then we're skipping a space, and then we're going to go 2, 1, skip. Yeah, 1, skip a, well, it's actually starting over here because I'm continuing. 1, skip a space, and then it's going to go to 2, 3, and then we're going to come down here, and it's going to skip a space again, and we're going to go 1, 2, 3, 1, skip a couple, 2, 3, 2, 3, and that's going to continue on that series. But that is far, far from the reality of the problem. What if I decide to start from x? Well, basically what you'd be looking at here is not 1, 2, 3, but 1, 2, 3. And the series of logic that would go is 1, and then we'd skip a space, 2, 3. And in the orientation of all those different combinations, amongst an idea where you don't really know where the first position is, and it may travel from not in this perfect little grid space where it's always going to follow this mechanical, mathematical law of standards about this rule. It might be starting here, and the first move is over here, and the second move is over here. So 1, 2, 3, or 1, 2, 3, or 1, 2, 3 in every combination. That once you started that first move, and you defined a second move to it, that any logic, those two dimensions, are going to dictate the third position. That those ideas are then going to create a field or a frame or a series which needs some equation or some symbol to reference it without having to physically break down every single one of those moves. And you can't really do it mathematically like this, because I'd have to put that up there, and that's why this symbol is what this symbol is, and that's why that equals what that reference is. Because in a lot of cases you'll see this shape symbol. It kind of looks like a 6, almost looks like an A kind of a deal, over a divisible a division line with another one of them A6 looking dealios and an X next to it, or an R or a K or what have you. And what that reference is we're talking about we're talking about multiple states in multiple frames that divide under that same meaning or under that same frame, but I'm going to put an additional symbol next to it. And once you do that, they're no longer the same thing, because you think, how would I take that same number plus this same number and a multiple of it? You would reduce that equation so it's basically X, right? Or R or K or what have you. And by allowing this kind of system to work mathematically, basically I use the STEM equation of reciprocating. A is an abruptly long sequence of reciprocating terms, and AX is AX plus BX equals CX, and AX plus BY equals CZ. both forms of those are individually correct. I could take this and it references this. So this is A, this next one is AX, and this next one is AXBY to a causal CZ dimensional idea. And thinking about how what you're positioning here and how this whole thing is orientated to define what mathematically and physically you're really looking at there to describe what that is. Now, anybody, again, can look on a line and say, this is what I do at work in physics, A to B. And the reality inside of that system is you're looking at x's, dimensional points that really define irrational numbers that say, you're looking at superstring theory there. A between B is really dimensionally bound to say inside of that there are fractal systems, that I do this when I clock in, at the end of the day there's this, and yet there's tons of sub-processes with many points and dimensions and combinations of series of moves that make them up. And our brain just kind of uses logic to process this move to the next move, or having to go over there and get this other thing. But amongst ideas, it's a pretty straightforward process. You don't really, even mechanics, you have to fix something or break something. You're kind of looking at the parts that work to the broken thing. Electronics, there's going to be some, burnt out circuit, or how you would start battery to the next step, even though it's moving at the speed of an electron traveling through that. Basically just, AC, alternating current, which says it's not really moving one particle all the way through, but it's just this push of this right here. And yet the function under that idea, electrodynamically, thermodynamically, the laws of motion, how you're looking at everything in there, works quite simply. Then again, I don't really know how you guys look at that, so, I mean, drop me a note, give me a clue where you guys are standing on that idea. But realistically, you're looking at combinations under these ideas. It's a matrixing system. This is a grid set. This is a matrix with combinations and logic systems. On one side of the fence, the really super complicated one are kind of fairly easy comparatively. Think of a very simple one that's should be simple, right? A, and I give you next series here, and then it continues and follows through. Well, if I just give you numbers or something, and then say, well, what does that refer to in the real world? It gets super complicated. Whereas a very complicated one kind of narrows the spectrum of what things can be. It's got a lot of points, a lot of dimensions, a lot of stuff's going to fit into that. This thing with 4 steps, and it's got to be big like that, can kind of be hard to function like that. And it gets even more compounded when you say A, X, Y, Z. Things like that really are difficult because you get into some extremely complicated thinkings about workings of the universe and processes and the entanglement system and superpositions, and these ideas of how you integrate into what you're doing every day and how that functions dimensionally. Am I A? Is that thing X? Is that thing X and I'm A? And the orientation of how these things, because they can be both. The mathematics says, it's not just one of those and I'm going to pick a dimension on those. It's going to be both of them at the same time. And I have to define some kind of equation, some kind of language that's going to define what that reference is. And a lot of times in mathematics we use things that most commonly, product rule, integration systems, Schrodinger's equation in quantum mechanics, field theories, UTF, unified field theory there, or the QDF, quantum dynamics theory, QDT. So, and a lot of them equations out there can define what that reference is if you know what you're looking at. So I just wanted to put some of that out there. And again, I use this one for prime systems, defining, the grid state to find a pattern in prime numbers. There's a lot of different. You start with 1, then you go 1, 2, 1, 2, and you just by doing that and trying to define some kind of logic system so you don't step on your own toes and make the same grid set and make the same orientation of those combinations. Think about what you do every day. Think about how you're problem solving. what are you really doing? So, I want to throw that out there. Catch you on the next one.